In section 9.5, we discussed the topic of chemical equilibrium. So a system where the forward and reverse reaction are occurring at the same rate is described as being at equilibrium. To indicate that a reaction is at equilibrium, instead of using a regular arrow, we used an arrow where we have half-headed arrows pointing in either direction. So what does it mean? Well, what it means is that when the reaction is at equilibrium, as fast as the reactants are being consumed, the products are turning back into the reactants. So I'll try and give you an example. When the system is at equilibrium, the amounts of products and reactants is constant. The reason being, as fast as the reactants are turning into the products are being converted back into the reactants. So think about a parking lot where the sign is flashing full. And well, what's happening? Well, the parking lot is always full. And the reason is because cars are leaving just as fast as they are arriving. So it's not always the same cars that are in the parking lot, but the parking lot is always full. There's a lot going on, people are leaving and people are arriving, but the parking lot is always full because those things are happening at the same rate. When a reaction achieves equilibrium, the amount of products and reactants will stop changing. Some reactions will achieve equilibrium after nearly all of the reactants have been converted into products. These reactions are said to lie to the right, that is, they favor the products. Some reactions are quite different. In some reactions, what we find is that very few of the reactants have been converted to products when we arrive at equilibrium. So this is an example that's given in your book, and you can see that when it gets to equilibrium, the amount of reactants exceeds the amount of products. In these kinds of systems, we say that the reaction or the equilibrium lies to the left. A reaction that's at equilibrium can be quantified by the equilibrium constant, which we give the symbol uppercase K. The equilibrium constant for a generic reaction of A moles of A plus B moles of B being converted into C moles of C and D moles of D is written like this. K is equal to the concentration of each of the products raised to the power of each of their stoichiometric coefficients divided by the concentration of each of the reactants raised to the power of their stoichiometric coefficient. So note that when we put the formula of something in square brackets, that is equal to the concentration of that substance in units of moles per liter. The exponents that go into K are going to be different every time for every reaction because they represent the stoichiometric coefficients of the balanced chemical equation. The important thing about K is that the bigger the value of K, the more products that are formed in the reaction. And these are kind of the general rules of thumb. If K is bigger than 1000, we have almost entirely products. If K is less than 1 over 1000, or 0.001, we have almost entirely reactants. If K is between 0.001 and 1000, then we're going to have significant amounts of both reactants and products. So here's an example of how we calculate K. So we have this reaction here, 2NO2 is in equilibrium with 1N2O4. And then we have a table that gives the equilibrium amounts of each of the reactants and products. So the first thing that I'm going to do is write the algebraic expression for K. So it is products over reactants but we have to square the reactants because we have two of them in our equation. And so now I'm just going to put the numbers in that are represented by those formulas. So we have 0.00139 moles per liter of N2O4 and 0.0172 moles per liter of NO2. So when I put that into my calculator, I get a value of K of 4.7. For a reaction that hasn't yet achieved equilibrium, we could perform a similar calculation to calculate what we call the reaction quotient. The reaction quotient is calculated in exactly the same way as K, except for we just understand that the reaction might not yet be at equilibrium. An important thing to recognize is that a reaction will spontaneously move in the direction that leads to K equaling Q. When K equals Q, the reaction is at equilibrium and everything stops changing. Importantly, if Q is bigger than K, products will be turned into reactants. That is, we say that the equilibrium shifts left. If Q is less than K, then what will spontaneously happen is reactants will be turned into products. That is, the equilibrium shifts right. Of course, when Q equals K, we are at equilibrium and the concentrations of things will not change and the reaction shifts neither to the left nor to the right. So if we measure the concentrations of reactants and products and calculate Q, we can compare that with K and then determine which way the reaction will move to obtain equilibrium. So just recapping, if Q is bigger than K, then products will get turned into reactants. We say the reaction shifts to the left. And if Q is less than K, reactants will get turned into products. We say that the reaction shifts to the right. If Q equals K, we're at equilibrium and nothing will change. So let's have a look at this. It says the value of K for the following reaction is 4.7. Is a mixture of gases in which the concentration of NO2 is 0.025 and the concentration of N2O4 is 0.014. So we should think about how we will write Q. Remember, it is always products over reactants. We only have 1 mole of product, so we don't need to put an exponent there, but we do have 2 moles of NO2, so we're going to need to square that. So our concentration of N2O4 is 0.014 and our concentration of NO2 is 0.025. So putting all of that into the calculator, we get a value of 2.24 for Q. So now we're going to compare that with K, which was 4.7, and we see that Q is less than K, so that means the reaction will proceed in the direction of the products, that is, to the right. So this reaction needs to be left for a little longer in order to come into equilibrium. Okay, and that concludes the video on section 9.5.